Good morning, good afternoon, and good evening. Welcome to this presentation on automated did parser generation based on the Hyperledger Universal Decentralized Identifier URI specification and more specifically the master did-uri-spec grammar. Also note that the parsers live in a separate project here, MW Herman 2000. /did-uri parsers, and of course that's on GitHub. My name is Michael Herman. I'm an independent blockchain architect, and I live in Alberta, Canada. This is a picture from south of Manyberries, Alberta, southeastern corner of the province, south of Medicine Hat, and for those of you that know where Havre, Montana is, it's about an hour north of Havre. I work on blockchain projects probably 10 hours a day, and I have decades of experience with distributed systems of many types operating in hostile environments. The purpose of this presentation is to provide an update on the operationalized version of the master did-uri-spec grammar. In the previous presentations, the grammar would typically fit on one page, but as you operationalize it, as you make it executable, you need to backfill that with some additional rules, and we'll see that. And then demonstrate how that master did-uri-spec grammar can be used then to automatically generate the source code for an operational did-uri-spec compliant parser without any hand coding. So the ability to go from specification in terms of the did-uri-spec grammar expressed in A, B, and F notation to a parser that is capable of recognizing and creating a representation of any of the did use cases, generating an internal representation of those that subsequently can then be passed in downstream to an execution engine or perhaps an optimizer before it reaches the execution engine. And then we'll show examples of the use cases. In this case, we have over 44 different use cases, and these are based on the lower level did-uri-spec use cases, one for one. And then of course we'll look at the test results. The primary audience again is implementers and maintainers of did parser software that is compliant with the did-uri-spec grammar, including but not limited to anybody working with the decentralized identifier specification, people creating did resolvers, which is actually the next step now that we have an executable grammar. And then of course dids are used everywhere, starting to be used everywhere. So for example, the Hyperledger Indy Agent to Agent communication services is another particular. There's four main sections in the rest of the talk. There's the operationalized master grammar, some slides showing very step-by-step the auto generation process. Then we'll look at some of the use cases, then we'll look at the test results. So here it is. In this case, it's being shown in Microsoft Visual Studio Community Edition. It's an editor that supports development and testing in many languages. The domain for this particular parser is C#. The technology we're using, the parse2.com aparse parser generator not only automatically generates C# parsers, but also Java parsers as well. So here, coming back to the grammar, so this first screen here is the typical grammar, did-uri-spec grammar that I've shown many times before in previous in previous webcasts. The only major change here is in line 26. If you have, dollar option equals a value, this grammar now supports quoted values in addition to unquoted numeric values. So that's just a little bit of an improvement. And in terms of the characters that can be in the quoted value, line 32 specifies a much broader range of characters. So just anticipating the future, you could have dollar option equals quote virtually any string, close quote. And of course there's the transform character, hex 21, which is the exclamation point. In line 32, unreserved, PCT encoded, and other DLIMs, those are taken from the RFC 3986 specification, which is actually on the next page of the operationalized grammar. So RFC 3986 provides a number of predefined parts or components. This particular copy of that URI syntax rules is taken from the OASIS ISO OData Open Data specification, the BNF specification for OData, and I've just copied and pasted it here, the same process that OASIS used. Page grammar is just more of RFC 3986. Down near the bottom, or actually right in the middle, around line 97, 98, you can see the PCT encoded. You can see the unreserved characters. And what we're using for characters is very similar to what you see in line 109. The grammar, just for completeness, has some elements of 3987, also taken from the OData specification. Those are actually commented out. And then at the bottom, you find all the standard alpha digit taken from RFC 5234, which are ABNF core definitions. And that's about it for the operationalized version of the master did-uri-spec grammar. This is the one we're actually to create, to auto-generate the parsers. So very simple. It's a Java class library. Again, this is from the parse2.com website, and it's called aparse. I'm using, you can see there, version 2.5. So you just issue the Java command, the name of the Java bytecode archive, the name of the class containing the parser generator, dash language CS for C#. Again, Java and other languages are supported, and then you pass in just the name of the ABNF file. So this is the current version, or almost the current version of the did-uri-spec ABNF grammar. Most current version is actually 2019-04-09, I believe. So once you execute that, and you may get some errors initially, you might have spelling errors in your grammar, that sort of thing. They're fairly easy to troubleshoot and diagnose. And then here I'm using Visual Studio Code just to show you a list of all the files that parser generator creates. And here you see the actual command that was used, and it's using the 2019-04-09 version of ABNF. So every rule goes into its own source file. The parser.cs there near the top, that's like the main line that handles options on the parser command line, and then invokes different processes to execute the rules, and the rules are responsible for recognizing different parts of the grammar. And when we look at the test results, that'll become much more obvious. But that's just a sample of the output that you get from the automated parser. Here we see a few modifications made to a couple of the auto-generated files. Here in parser.cs, the main source file containing the main function, I added an option called test cases, and this enables you to pass in a file containing a list of test cases. And we can see that file being opened in line 95 and then in 96 to 108, looping over each line, each test case in the file, and then in lines 105 to 104, 101 to 104, calling the primary parse function within the generated code and passing that test case in there. And then in line 106, we take rule, which is the AST, the abstract syntax tree returned from the parser, and we call accept with this variable visitor. What accept does essentially is iterate over the abstract syntax tree, and for each element in the tree, it's going to call the function that's associated with visitor. So this is a way, for example, of dumping out the tree, tracing through the information in the tree. Here we see the displayer.cs file. This has one of the two routines for dumping out the contents of the AST. There's an XML one later on, further down in the Solution Explorer. But we can see here, as we visit each rule, we need to visit the rules, the sub-rules within each rule that matched. And so we see a loop there in line 348 to 364. And there's some rules we're not going to dump out, like we don't need to see the tracing of each individual digit in a number, or each individual letter in a name. So we're excluding those and then dumping out with some indentation and what have you. And we'll have a look at that output in a moment. Okay, so let's look at the test cases. So this is the file then of test cases. There's about 44. I guess the last one didn't make it on the screen. And just for convenience, these have been sorted alphabetically, but they could be in any order. And they correspond again to the what I call the lower level did-uri test cases. These are the most granular test cases. When we look at slides, what I call slides 45 and 46, those are what I call the high-level did-uri user scenarios. So where you see, for example, in 31, 32, and 33, those all look very similar. So I'd only take one of those and to put it onto slide 45 and 46. There actually is a few here that don't make sense, like the first one did : 13 did : XYZ : a did method. They're just kind of in there for completeness of testing. But you can see some rather complicated ones. If you look at number 8, we're invoking the transformer and then $path equals blog. So we're looking for a path to a blog type of article. And then we have a filter where we want version equals 4 and we want language to be either French or US English. And if there's more than one article that matches, we want to just take the top one. And you can see that happening there. So let's look at the test results. To run the test, the first thing we need to do is configure, well, one way of doing it is to configure Visual Studio to do the debugging for us, or to run the parser in debug mode. And so in the middle there, the first white box, you can see the arguments that the parser takes. So the rule we're trying to resolve against, the target rule, is did-uri. That's the topmost rule, conceptually the topmost rule in the grammar. And then this one's a little bit misleading because it has dash string did colon xyz colon 1 2 3 4 and the test cases option. Those are actually mutually exclusive, and the test cases option takes precedence over the string. So in this case, we're running against the test cases in the did-uri test cases 2.txt file, which was the name of the file that we just saw a couple slides ago. So this just simply says go and read every one of those did-uris and resolve them against the did-uri rule. To invoke that, you see at the top there that orange box, the green arrow, just click on that. It'll recompile the parser if it's needed, and then execute it using those parameters. And here we see some of the sample output. So this, if you look at the sort of the third line down, the one that starts with 1:, that's that complicated, the most complicated content ID did URL that I just highlighted and spoke about before. And then in the remaining lines, you see how that is actually parsed out. The numbers represent the depth of the element in the AST tree, the abstract syntax tree that's produced by the parse method. So we won't go through every line, but you can see in lines 3 to 4, that's actually parsing the did colon example colon 1 2 3 4 5 6 7 8. 2, it recognizes that it's a transform, and on the right of each of these lines you can see the rule that matched. So where it says bang $path, that's a transform, and then the line underneath it says it found the transform character, and then it found $path equals blog and the components of that option. And then we see the $filter and how that is parsed out. And then we see the $top and how that is parsed out. And then finally at the bottom we see the path, the /2019-03-01/lunch in Barcelona path, and then the last 2 items where that's broken down into segments. So that was that piece of custom code we saw in the displayer.cs. And of course, it's this structure then that would be passed to an optional optimizer and then onto an execution engine to run against your favorite ledger. I mentioned that there's also an XML version of that sort of displayer.cs, and so here you can get an XML structured output of the AST. In this case, it is a different did-uri. This is did colon xyz colon 1 2 3 4 transform $select ID equals key 1 in quotes. And you can see the details there. So you can find all of this code, you can find all of the test cases on GitHub in the MW Herman / did-uri parsers repository. Everything is there that you see here, including a copy of this presentation. So the next steps, well, one step that was always there is build and test the did-uri grammar, and we've done that with this talk. And then we're going to continue to grow the number of scenarios we support, and we're going to grow the outreach in terms of awareness, knowledge, and understanding. And we have a new one at the bottom. Let's go build a did resolver in the not too distant future. So if you have any questions, my name is Michael Herman. My email address is mwherman@parallelspace.net. You can also find me on Rocket Chat and Twitter and LinkedIn under the alias mwherman2000. So thank you for investing the last 20 minutes in this talk, and I look forward to learning about the scenarios where you want to use DIDs, and let me know how I can help. Thank you.